then pneumonia and X-ray manifestation. And we introduce the problem of bias and confounders. I will then go to the experimental design, to the preliminary results, discussion, and conclusion. So CNNs, deep learning, and in particular CNNs have been for a while proposed for medical image analysis, and some results shows that outperforms previous solutions and even specialists. As a result, it's becoming in a prominent technology for computer-aided diagnosis, and some companies are already starting them. So I will not go into the detail, but there are many disciplines from cancer to brain segmentations to classifications of retinopathy that have been employed. And the number of publications have been incrementally increased over the last years. But one of the things I'm trying to study in my PhD in general and in this paper in particular is that most of the solutions have been good at the level of being published, so it's working as a proof that this is able to work, but they are starting to fail when we try to apply this into the clinical context. And we are trying to understand why and potential solutions to this. So very briefly, pneumonia, it's an infection that affects one or both lungs. This is caused because the air sacs or alveoli are filled up with fluid or pus. This can be caused by several reasons, including community infections such as bacteria, viruses, or fungi. There are two main groups that are affected by this, are mainly kids under the age of 5 years old, as well as adults that are 65 years old of older, immunodepressed people, and people with other comorbidities. There are several ways you can use to analyze pneumonia, but usually this includes to do a 2D X-ray of the lungs. So here we see an image that is a normal case when the black area that represents the air is have low density, so it's black. But when we have this area filled up with fluid, the density increase, and we can observe that this area become white. So the analysis of pneumonia has been very important, and already in 2017, 2018, there were two big data sets released. But with in the last years with the pandemic, also many people try to develop solutions to analyze this with the final aim to try to detect COVID-19. What is bias and we I think is so important for this. So in the literature, we can find bias as any systematic error that is presented in the data and then is accessible to be learned by the model, and that may result in wrong predictive estimations. Very roughly, we can define two types of bias. In one hand, we have those that reflects social discrimination, and we don't want this model to be reflected. Or prominent cases are like algorithms that have been proved to be racist, like this one that tried to predict the risk of reincidence in prisoners in the States. But here I would like to focus on other type of bias, and these are the bias that are generated as a result of the collection process, also known as a selection bias. So something to have in mind is when we have the data and we try to train a network that we want to have the highest accuracy possible, we should not forget that this data was the result of a previous pipeline. This starts from the populations. They can affect which population are we imaging, the characteristics of the hospital, the characteristics of the machines, preprocessing, and so on. As a result, these specific characteristics can affect the image. For instance, if we have one image, like a chest X-ray, and we want to predict the diagnosis of one disease, the specificities of a protocol of the hospital can act as confounder in both. This is especially relevant when we change the protocol of the hospital, when we are trying to mix different protocols, because we are trying to mix different hospitals, or because we are trying to mix different data sets to train a model, something that is very common in deep learning. So in the case of COVID-19, several publications prove that most of the papers propose solutions that were not ready for its safe clinical use. And one of the reasons is because they have a high risk of bias. In our work, we tried to understand why this was happening, and we conducted a systematic review, analyzing one of the main sources, and is the choice of the dataset. In here, we see a temporal analysis of peer-reviewed papers that took, and we analyze which datasets they employed. Here in purple, we can see non-COVID, so cases that were took as a control. And the most common used dataset is one dataset called 1-2 kids, pediatric kids. So these are data that came from kids 1 to 5 years old. And in the cases that most of the people took for COVID were, of course, adults, because it's when the pneumonia represents a problem in the case of COVID. So why we think this is important? We speculate theoretically that if you are not considering this, it may be very likely that you are training what here we see in red as model 1, and the model is using the features specific to the age to classify it, rather than the features specific to the disease. And we know this is a problem, and we know that all the models have high risk of bias because of this, but we wanted to understand better if this is always true, and in which cases this has a stronger consequence. So to do so, in this paper, we propose to artificially simulate these scenarios. And we took 2 datasets. One is the dataset that we found it was the most common, the ones to women and kids. These are open datasets from China, from kids of the age 1 to 5 years old. The second dataset represents adults. This is a curated dataset, the RSNI dataset from American people. So here I would like to do a disclaimer. We are assuming that the main variation source is the age, but we are aware that these are 2 different datasets and maybe more things that should have in common. So this is something that we are just making the big assumption in this. So to prepare the data, we first put, they were a big class imbalance. So we did an undersampling to the minimum number, and then we keep 90% of the data for training and validation, and 10% we give to what we call external tests. This is always balanced, and we always go against these images. And then for the training and validation, we simulate 4 different scenarios. So balanced dataset means that we want to do a classifier between control and disease, but the control, 50% of the cases came from the dataset 1 and 50% of the cases came from the dataset 2, similarly with disease. Then for the 3 conditions, we have light, strong, and total. In the case of total, for instance, in total 1, all the cases from control came from adults, and all the cases from disease came from kids. And in light and strong, we have with 85% and 95% respectively. So then for this 90%, 80% use for training and 20% we give for validation, plus the 10% external data set that we keep for later. We use pre-trained networks. We train them for 15 epochs to analyze this. We employ the Lacy-Smith one-cycle policy, and we run each combination from 5 times, and each time the validation test was randomly selected. We also wanted to know if this is affected by the architecture, so we prove with a standard redness 50, tested 121, and Quiznet 101. Since we don't find significant differences in the architecture, all the results that I'm going to show now are based on ResNet 50, but please go to the paper if you want to see more details on this. So in the general evaluations, let's start first with the black one. We have the internal. So internal is against validation. That means that we are evaluating the network against a data set that has the same class imbalance that was present during the training. We can see here that more or less all the networks present a good accuracy, especially in the case of total confounding. They seem to have very high accuracy because we can say that they tend to overfit. But if we check now the blue one, that is the external validation, this is against a balanced data set, we see that the accuracy decreased a lot. So in the case of balance, we don't see that this changes a lot. This is as expected. But in case of total confounding, we see that the accuracy drops a lot. And then in the case of light and strong confounder, we see that drops, but we see that there is a lot of variations between the combinations 1 and 2 in both the light and the strong for both the control and disease. To understand this, we can explain this if we analyze this separately, observing how behave the children class and the adult class. So in this table, the dark colors represent that this combination was the majority in the balanced combination, and the light one, it was the minority. So we can observe that in the case of the kids, they do very well for the balance. In case of total confounding, as we saw before, it fails totally for the unseen class. But then in light and strong, we observe that the children class present less drop in comparison to the adult class. This explains why before we saw such a big oscillations. If we then compare the variations respect to the balanced data set for the control and for the disease, we see similar behavior, but we can observe that in the case of the disease, the variation is bigger than the control. But as I will present in the discussion, since these are preliminary results, we can speculate why this is like this, but we cannot confirm anything at this point. So for the internal evaluation, we see that the models report good scores when they are against confounding that has similar characteristics that the one that they were training. This can explain why if you just take a data set, keep one part that has the same effect, you can still have very good accuracy. But then when we test against the external evaluation, we saw that the models report in general very bad scores. This can explain why if you move the model to another hospital or you test against another data set and this confounding is not the same, it's dropping the effect. Then regarding the effect of confounding, we observe that in case of total confounding, as we expect, the model don't know enough information about this distribution, so the model is always failing in the unseen class. But in the case of light and strong confounding, we observe a big variability between these two data sets. Similarly, for disease and control, we also see that the disease is to be more affected, but also we observe big variability. So as conclusion of future work, we want to say that model robustness and transferability are key requirements for safe clinical models. This is especially important because it is already a problem that models are not working, and this is very important in high-stress domains such as healthcare. So these experiments prove that these results can have a strong effect. Regarding the confounding, how this affects the confounding, it seems that this can vary a lot based on the confounding effect, but also on the dataset characteristics. So we want to explore more why in some datasets it's doing better than in other datasets. We can speculate that in some cases the model is more robust or the dataset is more homogeneous or heterogeneous. One way to reduce this is if we can include metadata about each of the steps, so we can have this into account and we are aware of this problem, so we can design tests to be sure that we are not having a confound. And as a future work, these are very preliminary results, so of course we want to validate this. We are planning to extend this, including more confounding factors, as well as different imaging modalities and medical disciplines. Just to mention, there is an open position on my lab for postdoctoral research. So if you are interested, please feel free to check the website. Thank you very much for your attention.